week,
distance.
we'll hear from a colleague, a
algorithm
professor
for
at San Francisco State, who's going to talk to us about RFID networks. Today I have the pleasure of introducing you to Dr. Lee from UC Davis, who's going to tell us about the relevant regions for visual cognition. Let's welcome him.
Okay, so yeah, thank you so much for inviting me to your beautiful campus. It's my first time here. It's very lovely. And I got lost a couple of times, and the students were really friendly too. So thank you. All right, so today I'm going to be talking about my lab's recent work on visual recognition. So this is one of the subfields of a more broader field called computer vision, where we're trying to create computers or machines that can understand the visual world like we humans do, right? Okay, so in the standard supervised visual recognition pipeline, this is what happens. You have annotators who will go out and collect images, right? And then they'll annotate them according to what they want to train their models on. So for example, if you want to train a car detector, right, a system that can detect cars and images, then an annotator will collect images of cars and images that don't contain cars, and then for the ones that have cars, they'll draw bounding boxes. Okay? So these boxes that localize the car in each of the training images that they've collected. And then they'll create an algorithm that can learn from this training data and, given new images, automatically detect the cars in these new images. Would it be better to turn off the lights, or can everybody see carefully, or is it? It's fine. Okay, we'll just continue. All right, so this approach works pretty well in practice, especially with recent progress in deep learning. But it requires lots and lots of expensive and error-prone bounding box annotations. Okay? And because of this, it's not scalable. So for a few categories, you can imagine doing this. But if I ask you to create a system that can recognize 30,000 different objects, then you're not going to be able to collect so much data and annotate all of them. Because you typically need thousands of these kinds of annotated images. So instead, in the weakly supervised visual recognition pipeline, you have something like this. So instead of annotating the bounding box that localizes the object of interest, you instead just tag an image at the image level. So you say, this image contains an airplane, but I'm not going to tell the system where in the image the airplane is. And some other forms of weak supervision could also be something like this, where you say, this is an attribute, which is basically a property of an object that I'm interested in learning about. And in this case, it'd be smile. And you say, this person is smiling more than the right person. But again, you don't say where this smile property lives in the image. So you don't actually annotate the mouth, for example. And so this doesn't require these detailed localization annotations. So it's scalable. But at the same time, it's much more difficult because you're giving less information to guide the algorithm, right? But another benefit of this approach is that it's less affected by any human errors or biases. So today I'm going to be talking about two problems that our lab has recently worked on. One is on weakly supervised object detection, and the other is on attribute localization. And I'll first talk about our work on object detection. So in the weakly supervised object detection setting, you have annotators who will collect images of cars and no cars, right? But then this time, they're not going to annotate where the cars are in those car images. Okay? So then you create an algorithm that can automatically discover the relevant regions that correspond to the object of interest. Okay? So they might look something like this. So you might discover things that look like car wheels, or you might discover these regions that include the car but also the surrounding context, because cars often appear on road. So without the localization information that accurately delineates the boundary of a car, the algorithm might try to find these common patterns that essentially include both car and the surrounding road. And then once you've discovered these kind of regions, you'll then go and train detection models that, again, given new images, try to detect the car in these new images. So this is a much more scalable approach because it's much cheaper to just say whether an image contains a car or not, right, compared to annotating the bounding box. But it's much more difficult, and because of all of these various factors like occlusions, lots of clutter, which means that there's multiple objects in each image, and you also want your algorithm to be able to be robust to interclass appearance variations, which is saying that two different car, like let's say you have a Honda Civic that's red and then a truck that's blue. These are all cars, and you want your algorithm to learn about these properties, right? And without these kinds of bounding box annotations, it's very hard to do so. So previously, researchers have tried to create algorithms for doing this. And this is sort of the common failure case that they've encountered, which is that instead of their algorithm localizing the entire car, it'll localize on a very discriminative part, which means that it's very it's common in the images that are labeled as car and not common in the images that aren't labeled with car. So something like wheel is very sort of specific to cars. And as I mentioned before, the other type of error that commonly happens is that the surrounding background, which is co-occurring with the object of interest, can also be included in the discovered region. Because cars often appear with road, and if you don't have these type annotations, the algorithm just doesn't know that, it doesn't know that these pixels are separate in terms of semantic object to these pixels. Right? So it's grouping things that are just commonly occurring together. So in order to address these sort of weaknesses, right? Because if you train a detector using these kind of regions, then given a new test image, it's not going to localize a full car. Instead, it's going to try to localize a part or include the surrounding context, which is something that you don't want, right? So what we do instead is we also try to mine these regions that are frequently appearing in car images and rarely in the images that are not labeled with car. But then, given these discovered regions, we then look to video. Okay? And the reason why we want to look to video is because videos provide motion information, right? Which is a very strong cue for localizing full objects. So in video, you have these pixels that are moving together, right? And usually the pixels that are moving together are from the same object. So you can use this as a cue to create better localizations. But at the same time, images tend to be of higher quality. So if you look at videos on YouTube, usually they're much more lower resolution. They're blurry and so on. So you don't really want to take those types of imagery to train your models, because then they're not going to perform well on more higher quality images. Okay? So we want to take a combination of both of these domains. And so our main idea here is that we want to use the videos to improve the localization on images for training an object detector. So I'll just give you a high-level idea of how this is going to work, and then I'll go into more detail later. So we first mine these regions, right, that are discriminative. So they commonly appear in the images that are labeled with car and rarely in the images that are not labeled with car. And then given these, we then go to YouTube, right, and we'll retrieve a bunch of videos with the same label, right, car. And then for each of these videos, we'll take this region, right, and then we'll compare it to all the frames in each of these videos. And then once we find a good match, so let's say like this, what we're going to do is we're going to then retrieve these tracked boxes that were generated using a video tracking algorithm. Okay? And the video tracking algorithm doesn't need to know whether it's a car or some other object, but it's just going to generate these boxes around these moving regions. Okay? So once you've made a match, what our algorithm is going to do is, conditioned on this match, it's going to retrieve the corresponding box that's highly overlapping with this region, right? So it's going to bring back this yellow tracked bounding box, okay? And you can see that by doing this, we can obtain a much better localization of the car in this training image, right? And we're going to repeat this for each of the training images in our weekly label training set. Okay. Oh, by the way, so if you have any questions, just feel free to ask anytime. Okay, so the first step in our approach is the following. We are given these images, right, that are, in this case, in our running example, I use airplane. So we have images that are labeled with airplane and images that are labeled as not having airplane. And for the images that have that are labeled with airplane, we don't know where the airplane is in the image. So the first step is to just generate possible candidate regions that may correspond to airplane in each image. Okay? And we do this using an existing algorithm which generates around 2,000 regions. Right? So these are candidate regions that algorithm thinks might contain an object. Okay, so here I'm just showing you 3 possible regions out of around 2,000. And then for each of these regions, we're going to then describe them with a deep neural network. Okay, so what this is basically going to do is it's going to give you a representation of this region. Okay? So it's going to look at things like what is the color, what is the texture, what is the shape. For bigger regions, it's going to look at what kinds of parts are in that bigger region, and so on. Okay? Now, given each of these regions that are described with a deep feature, okay, we're going to generate clusters. So this just means that we're going to group the regions across the images that are similar to one another. Right? So here, I'm showing you just a couple of examples of what these kind of clusters may look like. So here you can see that in this cluster, right, which has 5 regions, they all look like they're part of an airplane, right? Whereas here, they look like trees and just background noise. So if we're interested in training an airplane detector, this is the type of cluster that we like, and this is the one. These are the ones that we don't like, right? And there's an automatic way to figure out which clusters are preferable. And we can do this because we know, right? We know the labels of the regions or of the images that these regions came from, right? So these regions are coming from images that are either labeled with airplane or not airplane. So this cluster, all the regions are coming from images that were labeled with airplane, whereas here it's a mix. And this makes sense because you can have an image that's tagged with airplane that has trees, but you'll also have images that don't contain airplanes and instead contain, let's say, cars or pedestrians that also have trees, right? So this is a cluster that we don't like, and we can just use the weak labels to identify them. And so we can rank all the clusters based on how many of their regions actually come from images that were labeled with airplane, right? And if we do this, here I'm just showing you 4 clusters, just 2 regions in each one. In practice, we have many more regions per cluster, but I'm just showing you examples. And you can see that the top 4 ranked clusters for airplane actually correspond to either full airplanes or airplane parts, or some that include the surrounding context, right? And here are some more examples for other categories. So this one's for bird. This one's for boat, this one's for car, and this one's for cat. So you can see that all of these clusters contain regions that are relevant to the object of interest. But you can also see that in many cases, the discovered regions actually don't fully and tightly cover the object of interest, right? So this is a good example where actually it happens, but then in many cases it's going to be just the cat face instead of the whole body, just the tip of the airplane. This one's including the water with the boat and so on. So this is the main limitation of existing work in weakly supervised object detection. right? So they proceed to train detectors using these kind of regions. And if you do that, you're just going to end up with detecting, just parts or including the surrounding context, which is something that you don't want. You want to have a tight box around the object. So the goal in this work is to improve the localization of these kinds of regions to look more like those where they're tightly fitting the full object. Okay? So in the first case, we removed the surrounding context, and here we've sort of expanded the box to include the full object. And so the way we do this is as follows. Right? So suppose that here we have two regions that were part of clusters that were ranked highly, right, for this image. And then we go to YouTube, we download videos that were also tagged with airplane. And then for each video, we're first going to generate these video object tracks. So this algorithm will generate these tracking boxes on moving regions. Okay? And it doesn't need to know that this is an airplane. So it's actually going to generate many of these tracks per frame. So here I'm just showing you two, but in practice there will be many. Okay? And that algorithm also gives a ranking for those tracks, so we can prune out the ones that are more likely to be useful. Okay? And then what we do is for each of these regions, we're going to compare them to every single frame and all the videos that we've retrieved that are tagged with airplane, okay? Right, in a sliding window fashion, which means that we're going to take this region, and then since we don't know here, right, where the airplane is, or at least the machine doesn't know, right? So it's going to compare all of these regions, right? And across multiple scales, which means that it's always also going to resize these frames. And it's going to do that repeatedly for every single frame, and then it's going to choose the one that produced the highest match, highest similarity. Okay? So here, this is a good match, right? It's getting the front of the airplane, right? And then conditioned on that match, it will then retrieve the bounding box that was tracked for this object, right? And it's going to bring it back. And we're going to do this again for another region, right? So this was one that was retrieved, right? And here's another region. And again, it's going to be compared to every frame across all of these videos. And then once it finds a good match, it'll then bring back the corresponding track box. So here I'm just showing you two retrieve boxes. In practice, we have many of these regions per image. And we also, instead of just retrieving the best matches track box, we actually retrieve the top 20. Top 20 best matches. So if you do that, this is what the heat map of those retrieved boxes look like, right? So if we overlay all those boxes onto this image, right, then this is the accumulation of the retrieved, the area that these boxes are covering. And you can see that it's localizing the airplane pretty well, right? And here, I just want to show you what the comparison of the initial mined regions versus our retrieved boxes look like. So these are for various categories, and these are the initial discriminator regions, right? The ones that correspond to those clustered regions, right? And you can see that, so let me see which one you can see well. Like here, for example, for the bird, it's not only getting the bird, but it's including all the surrounding like twigs and things like that. And then for airplane, it's focusing more on different parts rather than the full airplane. Okay? Whereas with ours, we get a much nicer localization. So given all of these retrieved regions, we then want to create a single box for this image. Right? So the way we do that is with an algorithm called the Huff transform, which is essentially a voting algorithm. And it's going to vote. So each box that's retrieved is going to vote on its bounding box coordinates, right? Basically the spatial extent that it covers in the image. And we're going to essentially choose the box with the highest votes. Okay? And doing this will give us one image. So it's still not perfect, right? It's still ideally, you'd want this box to include the tail of this airplane. But it's still quite good. And we're going to then use these kinds of retrieved boxes, which we call pseudo-ground truth, to train our object detector, which replace the standard boxes that a human would have to annotate, right? So we can get these boxes essentially for free. So once we have those boxes, then we can then take any object detector that's trained in the fully supervised setting. And in our case, we take the state-of-the-art technique called RCNN. Okay? And the details of this algorithm is not important because it can be replaced with anything that essentially requires bounding boxes for training a detector. Okay, so let me just show you what the results look like for detecting objects for various categories. So we tested on standard benchmark data sets, and our algorithm was applied on 10 different categories. And so the images that we test on look something like this. So you can see that it's not a very simple data set in that there's multiple objects in each image, right? You often have objects that are not in their sort of typical pose. So for an airplane, it'd be easier if it was side view, for example. You often have, occlusion. You have, people squatting, for example. Here's another example of sort of a occluded car within a not such a canonical pose. So this is a pretty challenging data set, and one other reason why we choose these data sets to test on is because all existing methods have tested on this. So we want to have a fair comparison. Right? So first, let me show you what the discovered bounding boxes look like on our training images. So this is, the first row is for airplane, then bird, boat, car, and cat. And you can see that our method is able to handle partial occlusion, clutter, and atypical pose. So here's one example which is quite cluttered, and we're still able to get the cat. Let's see, here's another example here. This is for cows, dog, horse, motorcycle, and train. And here's, for example, one example of a dog in a, I guess, atypical pose. We're able to get it. But of course, our method still has failure cases. And here are some examples of when our method doesn't do so well. So if there are multiple objects that are tightly grouped, spatially close to each other, then instead of generating multiple boxes for each of those object instances, our method tends to just group all of them as one object. So here, in this example, there's actually 2 cows here. And then here, I guess it's a little hard to see, but there's a bunch of airplanes actually, and it's just grouped them all as one airplane. Another example, or typical failure case, is when the images, so when the objects in the images look very different from the those same objects in videos. So when we try to retrieve the boxes, the matching is not so accurate. And so we can either retrieve boxes that are just focused on a part or include some background. So for example, here, in the YouTube videos, when you search for bird, you don't get many videos that contain pelicans, so it has a hard time getting good boxes for that pelican. And then finally, one other sort of potentially strange failure example is when you have 2 object instances of the same category, like this, these are 2 dogs. In the heat map, we get a good localization, but when we try to vote on one box, we just get something that's kind of centered. And the reason is because when the voting algorithm that we're using is essentially trying to find, it's essentially trying to find a peak in this distribution of boxes. Okay? And so if you have if you imagine having 2 Gaussians that are next to each other with 2 peaks, and if the variance of the search that you're doing in this feature space is bigger than the width of each Gaussian, then it can actually include both instead of localizing on one of them. So that's just, it's because we use an algorithm called mean shift. And there are ways to handle this through adaptive scaling, but we didn't try that. Okay, and so here are some quantitative results. Basically, you don't really need to parse these tables, but if you just look at the last column, this is showing the mean detection accuracy over 10 object categories. And higher numbers are better. And these are numbers from previous state-of-the-art methods, which all essentially try to just find regions in those regions that frequently occur in the positively labeled images and rarely in the negative labeled images. And they don't do any kind of localization improvement. So by looking to video and then retrieving these track boxes, which are better localized, we can train much more accurate object detectors. Okay, so let me move on to the second part of the talk. And actually, let me actually turn the lights on, because I think it'll be much easier to see from the back. Is it possible to turn these lights on? I think maybe
there's
even
one more. I think.
Yeah.
Yeah, that one. Maybe.
Some of the figures are a bit hard to see.
Yeah.
Yeah, even that one. I think. I think even that one, if you could turn it off.
No, the other way.
Off.
Off.
Yeah.
Okay. Great. Yeah, I think this is better.
Yeah.
Okay, good. Okay, so far I've talked about how to localize objects for object detection, and now I'll talk about how to localize attributes. Okay? So first of all, attributes are properties of objects. So you can say that, okay, here's an airplane, but you can also say the airplane is white, it's long, it's flying, blah, blah, blah. So all of these kind of like adjectives are what are attributes. And for human faces, you can, one example of an attribute is this human smiling or not, right? So the goal of weakly supervised attribute localization is that given images that are labeled only at the image level, right, saying, okay, this image contains a person that's smiling, we want to automatically localize the part of that face, right, that corresponds to that attribute. And the reason why we want to do this is because then this helps us to actually model the attribute. So if we want to understand whether a human is smiling or not, we want to look at their mouth, right? So this is why we want to do that. And furthermore, in this relative setting, so what we have is during training, we have comparisons, okay? So we don't have these binary labels that just say, okay, this person is smiling and this person is not. Instead, we have these comparisons that say this person is smiling more than this person. Okay? So that's the setting that we're going to work with. Okay? So just quickly, previous approaches to tackling this problem either required pre-trained part detectors or they had a human in the loop that was fixing the algorithm's errors. And then recent work in our lab actually didn't require these sort of other forms of supervision, but everything was trained in a pipeline fashion, which means that we first learn features, then we train a localizer, then we train a classifier. So everything was sequential instead of sort of jointly trained. And because of this, it was suboptimal and slow. So our idea here is we want to jointly learn everything together. And we're going to do this in a deep learning framework, okay? So let me just give an overview of what our sort of system looks like. So the goal is, given these kind of pairs of ordered training images, right, that say, let's say person A is smiling more than person B, we want to create a system that can automatically localize where that attribute lives in each image, and at the same time say how much the person in that image is smiling, okay? So this is the algorithm that we have, okay? What's going to happen is we have a neural network, okay, that takes in the image, And that neural network has two subnetworks. The first one localizes the relevant part, and then the second one takes the localized part and tries to produce a score saying how much the person is smiling. Okay? So this is a score that indicates how much this person is smiling. And to train this network, we have what's called the loss function that's just going to say if V1, right, and V2, if they're partial order, so in this case, the ground truth is that this person is smiling more than this. So if V1 is not greater than V2, there's a penalty, right? Because what the algorithm is predicting is different from what the human is saying, or the human annotator has said. So in that case, you have a loss that tries to change the network so that it does produce correctly that V1 is greater than V2. Okay? So that's the general idea. And if we sort of dive into more details, so some of you may have read recently about convolutional neural networks and these kind of things, deep learning. So I won't go into too much detail here, but basically we have convolutional neural networks. And what the first network will do is it's going to localize the relevant region. Okay? So what it's going to do is it's going to take this image, and then it's going to process it in some way where it outputs 3 numbers, which are how to transform this image to get something like that. Okay? And here, so what this network is doing is it's essentially learning a mapping between the pixels in this image to an output grid. So initially, this output grid would just be empty. And then what this network will learn through training is that for each pixel in this output grid, where in the input image should I bring the pixel from? Okay. So that's what this equation is just saying. Okay, so yeah. And the really interesting thing here is that there's no supervision that says, localize the mouth for smile. Nobody has said this, so this is not provided during training. The supervision is coming from what comes after this, which is the score of this region. So if that score for this region doesn't agree with the comparison to another image, right? The two scores, if they don't agree with the ground truth comparison, then there's going to be an error. And so that error is going to come back and tell you how to change the transformations so that this patch localizes on the mouth instead of something else. Okay. And so then we have a ranker network which takes the localized region. Okay. It also takes the full image because it still provides some global context, right? When you want to identify whether someone's smiling, it definitely helps to look at the mouth, so it's like essential, but then other parts of the face can also help, right? So maybe when you smile, your eyes get smaller or something like this. So you still want to have the global context. And this ranking network will take those two regions and produce a final ranking score. So you don't need to understand these equations, but essentially, like I described before, basically what this means is this is the ground truth comparison, and if the score of these two do not agree, right, with this comparison, then there's going to be what's called a loss or an error that is back-propagated through these networks to adjust their network weights. Okay? And it's going to be trained iteratively until those scores satisfy these ground truth comparisons. Okay, so to train these neural networks, we use a technique called backpropagation and with mini-batch stochastic gradient descent. Okay, so it just means that we're iteratively updating the network with these with groups of training images. Okay. So let me try to show you in more detail what the network is learning over time. Right. So what I'm showing you here is 2 examples of different attributes, right? Dark hair and smile. And in the first row of these examples, I'm showing you where the localization is at a given training iteration. Okay? So initially, it's like for smile, this initial patch is just starting, at this sort of random location, even for dark hair. And then over training iterations, it's going to try to, it's changing the locations, and then it converges to the correct location. So here, the same thing is happening. Okay. And this is showing a heat map of what the localized region looks like across the data set. And this visualization works because the data set that we use are these faces, which are roughly aligned spatially. So this is showing the distribution of all the localized regions across the entire training data. And the reason why, so what's happening is, if you think about like dark hair, for example, right? If you localize on this cheek, right? If I only show you that cheek, and I say, okay, does this person have dark hair or not? That's not helpful at all, right? In many cases, right? So essentially, then if you give this region to that ranking network, it's going to produce a score that's highly unlikely to agree with the ground truth ordering, right? So it's going to try to change its localization until it finds something where, yes, if you keep localizing on this top of the face, right, then when I compare regions that are localized on the top of the face, then that gives me a pretty good estimate of whether this person has darker hair than this person, and so on. So that's why the localization network is localizing to those regions. Okay, so then during testing, what we do is we have some new image, we pass it through our localization and ranking network to get a score. Okay? So we tested our approach on 4 different data sets. Here I'm just showing you the 2 main ones, which are faces and shoes. For faces, we have various attributes like visible teeth, eyes open, dark hair, smile, good looking. And then for shoes, we have attributes like pointy, open, sporty, and comfort. Okay. And so here are some qualitative results of our algorithm. So there are 2 things to notice here. Okay. This is for attribute smile, and there's 2 results. One is where the localization is, right? So in at least these examples, the localization is very accurate, right? And then the other thing to notice is the strength of the smiling in each of these people. So our method is also producing a ranking, right, that says how much this person is smiling. So you can see that as you go from here to here, the people in those images are smiling more and more, right? So, and here are some other examples. So this is for attribute bald. And you can see the localization is towards the top of the head, and then the people are getting like balder, right? This is for dark hair, and then this is for eyes open, where the localization is on the eyes, right? And you can see the eyes are also getting bigger. So for these kinds of localizable attributes that are conditioned on specific parts like the eyes, nose, or mouth, our algorithm does quite well. For more global attributes, which are harder to interpret, like good-looking or masculine, which don't really have like definitive answers, so we even don't really know exactly why somebody's good-looking or masculine. Our algorithm tends to produce larger regions that include the eyes, nose, and mouth, but it's still these results are harder to interpret. So here are some results for shoes. So for the attribute comfort, our method has figured out that if you have like high heels, it's going to be uncomfortable, right? So it's focusing more on the heel size. So you can see from here to there, the length of the heel gets shorter and shorter. This one is for pointy, so it's correctly localizing towards the front of the shoe. And for sporty, I think it's looking at whether the shoes have laces or not. And so here, these are quantitative results, just showing how well our ranking results are. So again, you can sort of ignore all these numbers, but if you focus on the last column, this is just showing the average accuracy. And the way we evaluate our algorithm is, for testing, we have testing pairs where a human has annotated that, okay, this person is smiling more than this person, and in this pair, this person is smiling more than this person, and so on. And our algorithm will also produce a ranking score for each of these images. So if our algorithm also says, okay, this person is smiling more than this person, right, and the ground truth comparison is also that, then it's correct. And if it's not, it's incorrect. So this is showing that in around 87% of those testing pairs, our algorithm gets the correct comparison. And compared to existing methods that essentially either don't localize the region or they don't jointly optimize the localization and ranking, we're doing quite a bit better. And this, with this algorithm, we're actually able to get the best results on 4 different data sets. And this table is just showing whether you need to combine the localized part with the global part, the whole image, to produce an accurate ranking. So overall, I mean, there's some instances where one is doing better than the other, but in most cases, combining the two gives the best performance. Okay, so just to conclude, I've presented a weakly supervised learning framework for visual recognition, right? And I've talked about 2 tasks. One was object detection, where we're tracking and transferring the localized boxes from videos for more accurate object detection. And then the second one was on attribute localization, where we tried to jointly learn the features, the localizer and ranker for each attribute. And the main, I think, take-home message here is that weakly supervised learning is nice because it reduces annotations, which are expensive and error-prone. And so it's scalable, and at the same time, it lets the data speak for itself because you don't necessarily want to constrain your algorithms to learn from what a human thinks is best for learning, right? So this is, I think, the advantage of weakly supervised learning. And with that, I'd like to just thank my students who worked on these projects, and thank you all for being here. And I'd be happy to take any questions.
We have time for 2 questions.
So when you were evaluating your weakly supervised trainer on the Pascal
Right.
local object challenge data set, I think that was.
Yes, yes.
Were you comparing to other weakly supervised trainers, or were you comparing to strongly supervised trainers with full bounds?
Right. Yeah. So all the methods that I was comparing to in that table were all weakly supervised.
Okay.
We also compared to fully supervised, and those methods do better. But on some categories, we're actually able to achieve results that are almost the same, despite the fact that we don't have bounding boxes.
You used as part of your process a strongly supervised trainer called KCNN or something?
RCNN?
RCN. So I mean, you really want the prior to say, like, that's as good as we could possibly do, as good as RCN is.
Yes, you could potentially create an algorithm that learns from a fully supervised algorithm's outputs.
Well, that's not what
is that?
I'm
Oh, that's not what you're
I'm
saying.
just saying, like, in the context of RCNN, was that
Yes.
being the best you could do?
Right.
Do you get close to that?
Yeah. So for some object categories, like car, we're able to get just a few percentage points slower. For some other categories, the difference is much bigger. So one reason behind that is because for the boat category, boats are usually surrounded by water, right? But for all the other objects in that same data set, none of them are surrounded by water. So if you train an algorithm to discover patterns that are frequently appearing in images labeled with boat and not in the other ones, in many cases, the reasons that you find are boat plus water, because water is also very unique to the boat category. And so you have things like that where it's just, because of the size of the data set, it's hard for a weakly supervised algorithm to do what you want it to do.
The size being quite small? There's not a
It's small. I mean, it's not. It's still around 5,000 images for training. which isn't that small, but if it's not covering all, all the different categories in the world. So, usually you have other objects that appear in water like whale or, fish and so on, but those are not present in that data set.
Thank you.
Any other questions?
Yeah.
On the first section of it, you're talking about individual images and identifying them. Is it possible for a weakly supervised thing to do two, like if you had a cat and a dog or a human being, could it identify both objects in one image?
Yeah. So we are actually doing that. So for cat, we'll process that image, but then for another category, we'll again process it. So that image will actually have multiple tags saying there's a person, there's a cat, there's a dog in here. And for each one, we'll process them separately.
And then would that also help with multiple instances of the same object, like multiple cows or boats?
I think it can, yeah. So any additional information that you have would definitely help. So one thing, with the same category, it might not help, but at least across categories, you can say that if the localized region for person is this one, then it shouldn't be highly overlapping with, car, for example. So you can add constraints like that. We didn't do that, but yeah, it's possible.
Thank you.
Okay, well, thank you.